So we are approaching towards the end of our course. We're gonna have 2 or 3 more sessions. I'll make sure on the last lecture we're gonna come back and review some of the materials we've covered. But other than that, perhaps we're gonna have 2 more lectures next week. So today we're gonna, talk about PAC learning. You've already been familiarized with the notion of PAC learning, but after you saw all of those different algorithms and specific methods in order to classify a cluster or find regression models, let's see how we're gonna come up with some theoretical foundation how to find an upper bound between the relation between your in-sample error and out-of-sample error. How we're gonna find a good sweet spot to stop training when it is considered as underfitting or when it is considered as an overfitting. So one of those lectures are going to be today, and then later on we're going to see that there is another way to characterize this, and that could be done using a bias variance model. Okay, so we're going to discuss that next week. So let's just have a recap on that familiar jar of green and red coins, or right. So we've been discussing it. We called out 2 different samples, right? One shown in green and the other one shown in red. So we mentioned that we're gonna classify or we're gonna characterize, let's say, the mu or we by in-sample percentage that they are drawn from those bins inside this jar, right? And we're going to call this in-sample, right? And using the hypothesis H, we're going to call it the in-sample error of the hypothesis H, okay? So those in red that are drawn out of this, so those green marbles in a jar are those that we've already had an estimate using their mu, right? We thought that, okay, 60% of those are green, okay? But those that we've taken out of this jar, so that's why we call it out of sample, and we've shown in red, right? We can characterize them as E of out of H, okay? So in this case, we have drawn 10 independent samples. So in that 10, we see that there are 3 reds, right? So 30% red, 70% green. So we were trying to understand a relation between E in and E out, okay? All right. So let's go back to the foundation of this course, which was the learning problem. So we started by characterizing an unknown target function. That target function was unknown, so let's call it f. We wanted to imitate that f using some methods to approximate f, okay? So let's call that g that we finally pick, right? We want to make sure that our g that we'll learn is going to be as close as possible to the unknown f. And we start by data, by processing our data, parsing our data, and in this case it was a supervised learning method. So we had the labels. So for each of those x's, we had a corresponding label y, and using a hypothesis set and a learning algorithm, we could come up with some learning method, and we would pick the best g from this set of all the h's, right? This g is the one that we think is going to outperform the rest of the h's in a big set of h, and that g, we hope that it's going to imitate the unknown function of f. So now, playing around with the training example, just like what you saw in the previous slide, depending on the way we draw samples, we're going to come up with some probabilities. So there are distributions that we can treat to as we face how we're going to pick some samples or some draws from the training example. So the closest we can get to a real learning problem paradigm would be this flow included that these training examples, we should apply some probability distribution on the way we pick those x's, okay? And this is the bulk of the focus on these few lectures that we have. So, you've already know what an in-sample or training error is. We were showing it by E of in, right? You would just have to compute a summation over all the pairwise errors, right? Where you would have a misclassification in a case of classification. So say your final G that you picked, you were trying to, see its performance and find its accuracy. So for those cases that your yi wasn't equal to G of xi, right? That was your final hypothesis, and that was a true label. So you had one pairwise error. So, and then summing them up divided by the number of times you've done that for your E of n, you're going to come up with the in-sample error. So the output of this pairwise error or error on example I would be either +1 in a case of a binary classification, which states that these two were not equal, thus there was a misclassification, and the other case, which was 0, which was a correctly classification case. Okay, so we could have shown this by just an identity function of I or 1 for those cases that yi wasn't equal to y of xy. This is G. I'm gonna make sure that I fix this. This is G. Okay, so far so good. And as an example, for the case of linear regression, we were trying to estimate this by another method. Like this is a regression, so we would have computed this by not just a classification method, by a square error. Okay, different ways. So let's see how we defined out of sample error, or E out, right? We call it test error. So test error, now we're going to have another issue to play with. Since we are drawing some, we are using a probability to test the accuracy of our trained model, depending on the number of times we draw that, and depending on the way we do that, we're going to have now an expectation variable here, right, in statistics. As you know, expected value of a random variable represents the average of a large number of, independent realization, right, of a random variable. So since we are trying to do this randomly, so we have to deal with expectation. So we show this normally with this E. So out of sample error is equal to the expectation of pairwise errors, right? Each of those times we had. So this is also I. Okay. So now we have to deal with the probability distribution over the x's that we are taking into account to have the test validation of that model, right? So that's why those x's are now coming from a probability distribution of P of x. Okay? And now we have to make sure there are multiple ways to do that, right? In a case that x is independent, right? Each of those draws are independent from each other. You recall we were treating them as IID, right? The classification error can be computed as the probability of those independent draws that such that the predicted value using the hypothesis G of x wasn't equal to y, right? So how are we going to come up with this? It's a pretty easy proof, and that's the case that when we want to have the classification error, right, to compute the out of sample or test error, we're going to end up in a classification case with two cases. So that's the first one. This is the first one, and this is the second case. Case 1, case 2. So we have to sum them up. We have to sum them up to come up with the final value, right? So for the first case, the expected value of identity y and g of x, given that y wasn't equal to g of x, it shows it represents a misclassified case, right? And then we add the other case that these were equal, so that was correctly classified. So if you expand on either of these, on the second case, when you have a correctly classified case, this expected value would be 0, obviously. So the output of this expansion would be just simply the first one, identity of probability of y is misclassified, plus 0, right? Multiply the probability of classified cases. And this will cancel out this, and then the final value would be simply as so E out would be the probability of misclassified cases for the case that the draws are coming out of an independent distribution, okay? Random variable and independent distribution. Now, given this paradigm, we can expand on these to come up with other notations for learning, okay? Because your misclassification rate was 0, right? So it's a probability that your out of sample test, which was drawn from an independent or IID distribution, right, is going to be equal to that, which is 0, because it is a truly classified, right? Because this error would be 0, right? A pairwise error, right?
Yeah, the expected value of that.
Right. Yeah. Okay. So let's just have some quick review on other definitions. So there's another notion called Bernoulli random variable. So it's pretty easy. So when you see that in reference books, it's just referring to some random variables that has two possible outcomes, right? In this case, we can have 0 and 1. There is another notion on top of Bernoulli is binomial distribution. So when we have a Bernoulli random variable, and then when we sum them up, right, in an IID manner, identically and independently, I always confuse this IID. Identically distributed and independent. Yeah. So when our drawn was IID Bernoulli, right? When we sum them up, we're gonna come up with binomial distribution. So when we use these two keywords, you know that a Bernoulli random variable has two possible outcomes, 0 and 1, and then when you sum them up in an IID manner, you're gonna come up with a distribution that is called binomial. Okay. So let's define a z, which is a random outcome. Okay. So the probability of z equal to 1 is mu, some mu which is unknown. Okay. What does z here stands for? So 0 if green was drawn, right? Going back to that marble jar of marble. So z is going to be 0 if green was drawn, and z is going to be 1 if red was drawn. So you see that we are talking about two possible outcomes for this, right? So that's why we call this z is coming from a Bernoulli definition of a random variable, and with a possible unknown outcome of mu. Okay. And of course, let this be an independent draws with outcomes. Okay. So better way, we can show that Z1, Z2 up to Zn are coming from an IID, and those IID has a Bernoulli of mu, okay? So these are just different ways to showcase that. So let's have a quick example. How can we gain some information out of this Bernoulli? For instance, assuming that mu was 0.6, right? So that the probability that this drown was equal to 1 is 0.6, 60%. Say we are having 9 draws, right? 1 to 9. So some of them are 0, some of them are 1, right? Now, if we go over these draws as an output, right, we can have an estimate of the mu after n draws, right? We just simply add them up and divide it by the number of times we had the draw. Okay? So what do you think could be the plot of Vn, which is an estimate of a random variable for the 9 iterations, right? When we plot them, they are pretty close around this 0.6, but not quite close, up and down, okay? If you treat this 1, so this is 1, and this is 0, right? They are just up and down, and if you just carry on going with more n's, they're centered around that 0.6, okay? I could have just shown them in a better plot, but yeah, this is not completely accurate. But they are centered around this 0.6, right? But not specifically and completely equal to 0.6. Now, you see that coming back to our previous example, 1 represents our in sample, right? And 1 represents our out of sample. So out of sample is completely dependent on the way we draw, right? Is it independent? Is it dependent? Or the number of those draws, okay? Are we going to just test it by 5 test sets, test images, test examples, or it's going to be a million, right? So these can define some upper bound and lower bound between our in-sample error and out-of-sample error. So there are so many techniques, and we want to find a way to find that upper bound and some relation between our in-sample error and out-of-sample error, because having defined those, we are able to find when our training model is going to be underfitted or when it's going to be overfitted, at what time we need to stop or at what time we need to carry on, okay?
So this graph is dependent on this output sequence. So let's suppose we have more zeros, then it would be more around 0.4 instead of 0.6.
Yes, yes, yeah.
So because right now we have more ones.
Yes, that's right.
So pretty much our goal here is assuming we don't have mu, our goal is to figure out what mu is using a bunch of sampling.
Exactly.
So eventually you'll get to the point where you're straddling 0.6.
Yeah, that's one way to look at it, yeah. Yeah, good. All right. So V of n is a random variable. So in general, in statistical methods, we're gonna have 2 ways to estimate that, right? Using mean estimate on the left side, which we will focus here, using their expected value of V of n, and then this is gonna be the summation of all those outcomes, Bernoulli outcomes, divided by n and n times, right? And this, we hope that it's going to be close to mu, so the output would be mu, right? There's another way, school of thought, that you can estimate this without mean and by just variance when we are dealing with a random variable. So a variance of a random variable v of n is going to be the summation of all divided by n And then another way to compute that is 1 over n square variance of summation of all from 1 to n of z. And this number is always smaller or equal to n 1 over n. But for the sake of the completeness in this course, we're just focusing on mean estimate, okay? But there is another way to do that. I just wanted to bring this up so you know, okay? So we hope that this expected value of zi is going to be pretty close to that mu, okay? All right, let's see other properties. As you correctly mentioned, when v of n is approaching towards mu, it's as if we had drawn many, samples, right? So the more we go, the more we hire n, we can see that Vn is going to approach towards mu. All right. So now, how are we going to find a relation between these two? So we can characterize it this way: the probability that v of n minus mu, right, the absolute value, so the difference between your Vn, your random sampling, and the actual mean of the distribution that you've drawn out of, is within a margin epsilon. Okay? And this goes closer and closer to each other to the point that this epsilon is limiting or reaching towards 0, right? It's going to get diminished by the time that your n is going towards infinity. So when you are drawing so many samples, or when you're testing it with a lot of test images or test data, you can assume that this error is going to be minimal, right? So with probability of 1, so with a high confidence level, and we define exactly what confidence level is again. So with a high confidence level, we can be assured that this is within this range, mu minus epsilon and mu plus epsilon, somewhere around that, right? Here you can have a look as well. So you can see that this is around, right, some pluses and minuses. So this is mu plus epsilon or mu minus epsilon, right? This shows a range for us almost. Yeah, it was there. So this is one way to look at it. Now, can we formalize it better? In 1860 something, so there was a Russian mathematician called Chebyshev. So he come up with this inequality, which was later known as by his name. So it can be used as an probabilistic inequality. It provides an upper bound for the fact that we just discussed. Okay, so the absolute deviation of a random variable from its mean will exceed a given threshold. Okay, intuitively was just what we discussed. So random variable Vn, we can compute it as the summation of all those Bernoulli draws, right? The outcomes 0 and 1s divided by n, with a variance that is smaller than 1 over n. We mentioned it 2 slides ago. So we can assume that the probability that this Vn minus mu is bigger than that epsilon, that differences, is going to be always smaller than the variance of Vn divided by epsilon squared. And that itself is equal to, using this, is 1 over n epsilon squared. So this Chebyshev inequality give us a very rough upper bound, right? So you see, the higher the number of n is, chances are that we're going to get closer and closer. In the previous lecture, we talked about confidence intervals, right? I showed this to you guys, that using in a Gaussian and normal distribution, the range between mu plus sigma and minus sigma, so that the first confidence interval can be computed as a probability of your x's, random x's, right, coming from an IID distribution. And if you compute that on average, it's going to be showing you 68% of your distribution of your data, right? This area, this x. If you go from 1 sigma towards 2 sigmas, it's going to show around 95% of your distribution. So you can expect that 95% of the distribution of your x's are going to be centered around that plus 2 sigma minus 2 sigma. And if you add the third one, it's going to be shown around 99.7. And I was telling you that there are so many statistical tests that you can, test. First of all, if one sample was drawn from a uniform distribution, or you were computing two samples if they are equally coming from a normal distribution or not, using a null hypothesis. And that was called a student t-test. Perhaps you've already used it in other analysis. Okay. So using that again, that background, and also adding Chebyshev inequality, so we can say that this mu minus epsilon and mu plus epsilon, right, and the upper bound that it gives us, that is smaller than 1 divided by n epsilon square, is showing us the area of the shaded region. So right here, you can compute the exact area by a simple integral, or by a probabilistic method, right? You know that on average what's going to be inside this or outside this, right? And this is exactly what is called a confidence level, right? We show this by delta. So 1 minus delta, which shows exactly here, right? It shows exactly here, is equivalent to a confidence level. So in papers, when you read that we have tested the confidence level of this experimental setup, and with 95% confidence level, we can show that this was drawn from a specific distribution, right? And that exactly says that all those variables that they have tested were around this distribution, mu plus 2 sigma and mu minus 2 sigma, because it's going to show around 90%, 95% of the distribution. Okay. If you go higher and higher, you have a higher confidence level that your x's were around this, so your experimentation was sort of robust. Okay. Some might say 99%, 90, but the norm normally is 95% confidence level. All right. So the way you can define this is pretty easy. As an example, if your delta was 0.1, thus 1 minus delta is 99%, right? So you can easily compute your epsilon using this formula that's given here. And your epsilon would be the square root 1 divided by 2n and log of 100, which is around 1.63 divided by n. And we don't care about n, we can just have an upper bound. So if your mu is here, your mean was here, you can assume that these two distributions are around mu plus this and minus this. Okay. Can anyone suggest what are these two lines? I mean, later we're gonna see. Do these give you any hint? The blue and green? Say that again?
Mu plus epsilon.
Yes, so I'm just asking, do you know concretely how we can call these two lines, the blue and green, the blue and red? I mean, later in this lecture we're going to see. Because using Chebyshev, we're going to have that range, right? Mu plus. And this is the n, right? The more we go higher, these two are going to get closer and closer. No. Okay, we'll see. We'll see in 10 minutes. Okay. So we saw this Hoeffding's inequality 100 years after Chebyshev. The other mathematician, perhaps in 1960s, they came up with this inequality. So you see, this is very rough upper bound. We need more information. And he was basically saying that in a big sample or a large n, mu is probably going to get close to nu is probably going to get close to mu, right? Or v going to get close to mean within an epsilon. So he was trying to characterize the inequality this way. E of minus exponential minus 2 epsilon square and n, okay? And then we discuss the first instance of definition for PAC as the statement mu equal to nu, right, is PAC, probably approximately correct. And that was the first notion of PAC learning for us. Okay? So if we carry on taking draws, we are hoping that the average mean and the mean of those out of samples, right, are going to get close to each other. Probably approximately, they're going to get close to each other. Now, let's plug Hoeffding's inequality to those random variable and the outcome. So that was v of n, 1 over n of the summation of all those z's, right? And the z's were coming out of an IID distribution of Bernoulli with a mean of mu, right? So plug them here. We're going to have the probability of Vn minus mu greater than epsilon with an upper bound that Hoeffding's inequality suggested. You see that this is exponential decrease in n. So coming up and finding the delta, defining delta as this value, we can compute delta this way now. 1 over 2n log of 1 over delta. Okay? Okay. So recall we had in-sample error computed as an identity of yn not equal to h of xi's, right, and divided by n for n number of times. And out-of-sample error was the probability of that those h of x's that are coming from an IID are going to get close to mu, okay? Now, let us assume that a hypothesis function, right, that we were using was a fixed hypothesis, okay? And we selected that hypothesis in order to tackle our learning problem before we observe our data set D. We didn't have any knowledge. We just selected, oh, okay, we're gonna use that specific edge for this problem without even seeing the D, okay? So the possible outcome would be, again, 1 and 0, right? It's a Bernoulli variable. For the cases that was a misclassification, and else for the case that it was a classification, okay? Now, we have all these z's for all of those n's because we had n draws. Now the claim could be when we have n z's, z1 up to zn, and they're coming from an IID, right? And Bernoulli of mu is a random variable. So we can define finally that for any fixed edge, right? Any fixed hypothesis, this hypothesis of x of f of x up to the xn of f of xn is an IID sequence. If we don't see the data set, right, and we chose a hypothesis, so the output of that, the outcome of that hypothesis would be an IID itself. Any questions? I guess you like neural networks more, right? So, claiming this, the identity function that corresponds to the misclassification of either of those x's from x1 up to xn is also coming from an IID sequence. And using Hoeffding's inequality, we can plug it into that, and we're going to say the in-sample error of hypothesis H minus out-of-sample error of hypothesis H are within an epsilon, right? The absolute value of are at least within an epsilon, and the probability of that being within an epsilon is going to be smaller or equal than 2e minus 2 and e squared, okay? Remember, we call this delta. And plug in the confidence intervals. So we can say that with probability greater than 1 minus delta, these two are close to each other within an epsilon. And that value of epsilon could be this. Okay? Another way to represent the problem. Or your out-of-sample error is always smaller than your in-sample error plus this. So now you can sort of visualize why normally your out-of-sample error is higher than in-sample error when you train models. All right, so remember when I was talking about using those hypothesis functions without seeing data, right? When we were trying to use those, so we assume that those are fixed hypotheses, okay? But normally when we come up with the best hypothesis and we call it G out of those H's, so that G is not fixed anymore because we wanted to have the best output, best accuracy out of our model training. That's why first the H was a fixed hypothesis, right, before observing data. But afterward, the final hypothesis G, that is the best performing G, best performing among those H's, and we call it G, is selected after we observe D. Okay? Why is that? Because simply we want to keep E of n of G small, right? We want to have the best training outcome when we train a model, and we want to use the best G to accomplish that, right? So after seeing the data, after observing data, now those G's are not IID anymore, right? Does that make sense? Because they're not independent and identical, right? So for this problem, Hoeffding's inequality cannot be applied. We can only apply Hoeffding's inequality with the case that the H's were fixed without observing the data. But normally, anytime we want to pick something, we pick the best G out of those H's, we call it G, and that G was after observing. So how are we going to do that? How are we going to generalize this, first of all? And then when we have multiple of those, so for multi-bin problem, how are we going to generalize it to multi-bins as well, right? So you see, starting from Chebyshev and then Hoeffding's inequality, there are still issues to be answered depending on the property of our hypothesis, right? So like, if you have multiple bins now, each of those bins, right, are corresponding with one H. One hypothesis can define this. Bin 1, we have hypothesis 1. It has its own mu, right? And it has its own nu, right? The one that we took out of it. Another jar of marbles, we have another hypothesis to tackle this, to learn this. It has its own mu and nu, okay? So how are we going to answer this when we have m of those, right? We have from 1 up to m bins. How are we going to expand and generalize Hoeffding's inequality for multi-bin problem? That's why we need to just go higher in our upper bound. What we can say is finally the probability of En given those G's that we figured after observing data is going to be always smaller than, so remember this is the final hypothesis, smaller than probability of the absolute differences between your En and E out of the first bin using its first hypothesis, right? Or the second one, so this is or, remember, or the last one, mth one. Okay? So the probability of this, or this, or this, or this. So if we are talking about some or of some probability numbers, so what we're going to do, m times, we need to have a union over all of those. So the summation of all of those probabilities from m from 1 up to m, and then we're going to come up with this. Instead of 2, we have to plug in that summation to the previous upper bound now, right? And we're going to say that if we have multi-beans and we are trying to find a final hypothesis, Hoeffding's inequality, in order to answer this, we need to plug in even a higher number now. So now our upper bound is even higher now. So it gives us a lower sort of accurate upper bound because it keeps expanding to the point that perhaps we knew that, okay, the difference is that high already, right?
So we have similar epsilon for all the edges. I mean,
For each of those, yeah. Oh no, actually, it's not a similar epsilon. It's epsilon. Yeah, good observation. Yeah.
like when we are doing a summation, we are just assuming that all the epsilon.
Yes. Yeah. Taking the highest one. Yeah. Okay. This is just the way we formulated the union bond formulation to come up with this. So I'm just gonna quickly go over this. You can have a look at it later. So finally, we know that if G is coming from edge, right, and it was selected after observing your data set D, then Hoeffding's inequality bound is going to be weakened by a factor of m, because we need to add that m in order to estimate that correctly. And then using this is going to give us a way higher factor, so the accuracy of the upper bound is actually weakened. Okay. So playing around with that formula, so you're going to see that the absolute addition of in-sample error and out-of-sample error of your G is always smaller than or equal than that very first range that you saw when we were drawing that 9 times those coins. Okay, but the factor that has changed is that m here, right? So finally, we can just call this a delta G, a difference between your in-sample and out-of-sample error. And then we call this, finally, delta G is within the root square of 1 over 2n and the log of 2m divided by delta. Okay. We'll see the differences between these two with just 2 examples that we're going to see in the next 2 slides. And then I'll wrap up the class.
This we have one equation plus and one equation minus.
Oh yeah. Yeah, it should be both minus. Okay, so let's have a very simple question. We have a fair coin, okay? We toss it 10 times. What is the probability of getting heads? Actually, 10 heads when we toss it 10 times.
1 upon 1, 1 upon 1, 0,
2 to the power 10. 1 upon 2 to the power 10.
Yes. So we have to account that 10 times. Why you power that to 10?
So we have independent and we have just minus.
Because each of those tosses are independent from each other, right? So they are IID. So simply 10 times, 10 independent outcome, and then it's going to be around less than 1%. Okay? Now, question 2. If you toss a fair coins 1,000 times, I'm sorry, if you toss a 1,000 fair coins 10 times, so let me just 1,000. If you toss 1,000 fair coins 10 times, right? What's the probability that some coins get 10 heads? So now instead of one coin, we have 1,000 coins, and each of those we're gonna toss them up 10 times. Okay. So now what's the probability of getting some heads? 10 heads actually.
So like none of them are getting, then we can have at least one something.
How are we gonna approach this? So we need to compute the probability of at least 10 heads on one of the coins, right?
Minus none of them getting,
Okay.
and at least some of them.
Okay. So how are we gonna compute that?
Yeah.
So yeah, so far good.
So it would be 1 minus none of them getting is like 1 minus calculated computer.
Okay. Okay. We're getting close.
And then we have to multiply power by.
Okay. Okay. So now we have 1,000 fair coins, right? We toss them all 10 times. Now, in order to compute the probability of at least 10 heads on one of the coins, right, it's going to be equal to 1 minus probability of each of those 1,000 coins come up tail at least once, like the other complementary side of the problem, okay? Duality of the problem. And if you have, just like your colleague said, it's going to be 1 minus 1 over 2 to the raise of 10, but we have this for 1,000 coins. Now look at the differences. It's 63%, right? While on the other side, you had less than 1%. So that's why if something can go wrong, it will go wrong, right? When you have multiple sort of outcomes, and if you add them up, you're going to have a way, way, way higher chance, right? That's why for multi-bean and those cases that are not independent, so you have to factor in their corresponding, m, or in this case, we need to factor in all those 1,000 fair coins. So that's why your range will be weakened by a large margin. Now it's 63%. Okay, and that's the error that we call it as error of generalization, right? So now we have an m, which is the number of bins we have, and we have n, which is the number of data in your data set. So we have two variables now. So delta G was the difference, the absolute difference between your in-sample and out-of-sample error, right? If you increase m now, you see that the delta G is increased because you have multiple, for instance, multiple fair coins, right? It's going to hurt you if you increase m. But in general, your in-sample error will decrease because you have a higher chance of getting a G. On the other side, if you increase n, your number of data in your training set, normally this decreases, and it's good for you because your in-sample and out-of-sample error are getting close to each other. But on the other side, if you increase n, your training error might suffer, right? So now we are having a trade-off here in a generalization. And that's how we can define for a fixed n, if you put n as fixed and you make m variable, right? You can define your underfitting and overfitting area, region of your graph. The blue line that I asked you some minutes ago was representing your out-of-sample error, right? And this represents your in-sample error, okay? And later on, we're going to see that what's going to be normally the ideal choice of m given n was fixed? So now let's have n as variable, right? So now you're going with so many test sets, right? And the more we go higher, you're going to see that we start from overfitting and then we go underfitting, because the in-sample error, as we go along, it's going to mildly increase, but for sure your out-of-sample error is going to decrease. You understand why when we go higher, we're going to have an underfitting here? So, as you saw that through this lecture, Hoeffding's inequality doesn't give us a very, very accurate upper bound. That's why there is another notion called bias variance that we discuss later on in the course next week, to use bias and variance of a distribution to come up with the generalization. Okay. So the main issue is, for most models, H has infinite number of hypotheses. Given the simplest case of perceptron, you can have infinite H, because for a simple case of classification, you're going to have multiple or infinite ways to classify that, right? You had like this data, pluses were here and minuses were there. So there are infinite ways to classify them, like H1, H2, H3, H4, infinite way, right? And that was the issue. And perceptron is like the easiest model. So expanding to other more sophisticated model, you're going to see that for most of the models, H has an infinite number of hypotheses. So choosing M would have a clear outcome to the training and test error. Okay? Any questions?
I had a question on the